Okay, let's continue. All right. So the second half will be a pleasant, I hope. All right. So we are going to look at the Kirchoff's rule now. All right. And this is, I think, something that I mentioned about the recipe in the sense that once you understand how to apply Ohm's law, okay, and understand how the current flow, what's happening at the junction, because you sort of saw what is the parallel connections do with the current flow, and whenever you have a series connection, the current just keep going. So that's allow you to understand these two rules by Kirchoff. All right, and this eventually allow you to do the multi-loop circuits analysis. All right, so I'll show you with examples. That's the best way to see it through how this is being applied. Okay, so the Kirchoff's rule are actually composed of two parts. One is the junction rule, okay, and the other one is the loop rule. But even though it sounds like a rule, but it's actually very simple rules to understand. The junction rule, the name is implied that it's going to use at the junction. And we have already seen every time there is a junction, the current the current has to split. Okay, so for example, if there is an incoming current into the junction A, as you can see right here, all right, so the current has to flow out. So if you have two currents flowing out, in must be equal to out because of the conservation of charges. That's it. That's a junction rule. It's a simple intuitive rule. The total current in must be equal to the total current out. Done. Second one is also makes sense because second one is regarding the potential. And every time that you talk about the potential, okay, once again, you have something here. And if you move up, you get to the higher potential. But then if you bring it back down to the original position, you come back to the original potential. So that's the whole idea. So that means the potential across every element, you just go through whatever you can go. But eventually, if you arrive at the initial point, you're going to have to come back to the same potential. That's the reason why they say if you have something that's sort of like come into a loop means you loop back to the original position. No matter what you have experienced along the way, you sum those up. The potential difference across the whole path that you have gone through must sum up to zero. Make sense? Because you arrive back at the original position, there's no change. Okay? So if I want to bring sort of this topic back to the day of the energy, it's going to be the same thing as the potential energy. If I want to bring this back to the thermodynamics, it's going to be the same thing as the internal energy. So every time you come back into the loop, the total internal energy is going to be the same. Same idea. Because the potential that we are talking right here is the same as other potential. Okay, sounds cool? So what you have over here is if you pick a loop, potential difference across all the elements along that loop, inside that loop, must sum up to zero. That is the loop rule. When you combine these two rules, that is the Kirchoff's rule for multi-loop circuit analysis. All right, and I'll show you how it's done right here. So the point of applying this one is simple. You combine this with the Ohm's law. That's, as I said, there's only one thing that you can do. V equal to IR. That's all you care about. Okay. Well, that's not all you care about. I mean, that's all you're going to need to use a lot. All right. Plus, because in the loop rule, you have to collect all those potential difference across all the elements in your circuits. But it turns out in your circuit, when you look back here, what kind of elements you get up to this point? Well, Ajahn, the element in the circuit, it's either the resistor or it's the battery. There are only two elements in your circuit at this point. So if you know how to evaluate the potential difference across these two elements, the resistor, the battery, then you know how to apply loop rule already. Okay, so here's the key. Every time that you going through a resistor that having the current flowing through, everyone knows that the potential difference across is going to be just I times R. Everyone with me, yeah? However, you have two choices now. You want to talk about A to B in the sense that the current flow from A to B, or you want to talk about A to B when the current actually flow against you. When I say against, mean you're going from A to B in the same direction as the current, or you go from A to B against the direction of the flow. These two will give you opposite potential difference. You guys with me? All right, because the current flow from high to low. So if the current flow from left to right, so that's mean A is higher potential than the B. So the potential difference is going to be negative because you're going from high to low. Potential is negative. On the other hand, if you go from A to B, but then the current actually flow backward, so that's mean at B has a higher potential than the A. So going from A to B, you are going higher in potential. So the potential difference is positive. See, simple, yeah? There is another element. It's just the battery. So the battery is good because you don't need to use Ohm's law or anything. The polarity of the battery is already telling you which one has a higher potential. If you connect point B to the positive polarity of your battery, so this is definitely going to be high and this is going to be low because the point A is connecting with the negative side of the battery. On the other hand, of course, if you put A onto the positive ends of the battery and B to the negative ends, this is going to be high, this is going to be low. So once you talk about the potential difference, in the case of the figure C, potential difference is going to be positive because you're going from low to high. In figure D, it's going to be negative because you're going from high to low. Nice. Okay, so these are all summaries of the 4 cases that you're going to face. Okay, it's either Ohm's law, IR, or it's either battery. But the key is the directions of the flow or the polarity of the battery. That's important because that will give you the opposite sign. Okay. All right, so I will do this. Let's apply this to the actual circuit and see how it goes. Let's go through this simple circuit. This one actually you can do without doing the Kirchoff's rule, but I'm going to show you how this rule is being applied right now. Okay, so here's the point. I am proposing the way of doing this in a systematic way. So what I'm going to do is this. I'm going to try to do the loop rule because this one there's no junction. Okay, so I'm going to apply loop rule and I'm just going to go through a loop. So you pick a loop because this one there is only one loop that you can see. It's A, B, C, D, A. A, B, C, D, A. That's my loop. The only things that you can do with this one is just doing the delta V around this loop. So what I'm going to do is, so I'm going to use, my saying is, I am going to analyze by walking through the loop. I don't know you like this word or not. Walking along the loop. So that means I'm going to walk along A, I'm going to walk to point B, I'm going to walk to point C, I'm going to walk to point D, and then going to walk back to A. That's my complete round of walking. Walking means analyzing, of course. All right, and my way of doing this, just to prevent any mistakes, and it seems to work quite well for me for the past many decades, I guess. So what I'm going to do is this. This is my recipe, pretty much. So I'm just going to walk from A to B. All right, see. Now, sort of walk along with me. So I'm start walking, and look at the green ink over here. I hit the negative ends of the battery. It's 6 volts, so I put negative 6. That's my way of doing it. Just follow me for now. Keep walking, nothing happening, nothing is happening. Is about to. Now I hit the resistor R. Okay, but in this case, the current is being set to flow clockwise, the direction of my analyzing right now, I'm walking clockwise as well. So at this point, I am walking in the same direction of the current flow. I would call this my positive direction, pretty much. So it means I'm going along with the flow. Because now I have the current flow, I, with the resistance 8. So I'm going to say it's the 8I. That's Ohm's law. Potential is current times the resistance. But because I am walking in the same direction as the current flow, that's my positive direction. Keep going. Now I'm at point C. Now I hit the battery, but now I'm hitting the positive ends of the battery. I put the positive 12 to it. Keep going. Nothing. Now I see the resistor one more time, so I'm going to apply Ohm's law, current times resistance. So I'm going to do I times R2. However, because right now you can see that I am walking in the same direction as my current flow, so it's my positive direction. Now I'm arrived at my original position A. I equate this to 0. That's Loop's rule. I can solve this for I. I'm done. Sounds good? Okay, very nice. So I hope you see how Loop's rule is being applied. Even though you might find it like, Ajahn, what does it mean by walking? So actually what I'm doing is nothing more than just trying to collect the delta V along the way. Okay, however, by doing collection of the delta V, so I'm going to show you a official way of doing this. Okay, come along with me one more time. I'm coming from A. Now I'm use the blue ink. I just need to see what is the potential across A to B, right? Because right now from A to B, I have only single battery right now. However, from A to B, I'm going from the low to the high. This one is matching case figure C here. So actually, from A to B, I have positive 6 volts. You guys with me? Okay, positive 6 volt. Now, I have to go from B, keep going, to C. So from B to C over here, the current is actually flowing down. Okay, I going through the resistor R1. So right now, this case looks just like figure A. You guys with me? Because the current flow from first initial point to the final point. See, here, my initial point is B. I'm moving to point C. My current flow from B to C. So the potential across this one is going to be, according to figure A, negative I times R. With me, guys? Okay, keep going. Now I'm arrived at point C. I want to go to point D dog over here. But now I'm going from positive end to the negative end. So this one corresponds to the figure D case. I'm coming from positive to the negative. I'm coming from high to low. So it's going to be negative 12 volt here. And then now I want to come back from D to A. At this point, the current is flowing up. Okay, so I am in the same configuration as figure A. I am coming from high to low. So the potential difference from D to A is going to be negative I times 10. Okay, now I'll complete the loop. I equate this to 0. With me, guys? All right, now if you look and compare between my equation in green, let me call this equation star, and you compare this to the bottom one, this is 2 stars, they are actually the same, okay, except of course with the negative sign across the equation. So it's the same as I multiply my 2 stars equation with the negative one, the whole equation. So I get my green one-star equation. Okay, so you see my proposal here. So you guys can follow the official ways of evaluating the potential difference. So you just go along with the 4 cases on the left. Or if you like my analysis, all I'm doing is, it seems kind of natural to me when I do the analysis, and then I'm thinking of like I'm walking along the loop. Walking means analyzing along the loop. And it seems to be, I don't know, from my own experience, it seems to make less mistakes when I just like, when I say, hey, I'm walking along this one, I hit the -1, I put the -1 to it. If I move along my current, that's my positive and positive directions of the potential difference. It seems natural to me. But when you do official one, it seems like you have to go opposite all the time, because when you go along with the current, you are moving in a lower potential direction. Or when you try to go from positive end to the negative ends of the battery, you're actually going to a negative direction of the potential difference. So that's why it seems like you have to flip the sign all the time in your head, yeah, to get the sign of the potential difference right. And seems like when you have to keep doing this extra steps of keep in mind that, hey, it's a negative change, sometimes you will forget doing this at some point. All right, so I try to avoid that. So that's why I try to, make the analysis kind of more natural. If you like it, okay. If you don't like it, that's okay. I mean, there's nothing wrong with either approach, okay. I think you can apply both ways, or just pick the one you like. Okay. All right. So with this whole idea, now I will show you how to analyze multi-loop circuits now. Okay. And as I say, it's just going to be one step more complicated, but other than that, it's going to be completely straightforward. Okay. Here we go. ครับผม
So I have a question about
Yeah.
why is I high to low again?
Why is high? Okay, so we agree that the currents always flow from high voltage or high potential to the low potential, like a water flow from high to low. Same thing as a current. Current always flow from high potential to a low potential.
Yeah, but how do you know that it's low?
How do we know that it's flow from high to low? Is that what you're saying?
Yeah.
How do we know? Okay, first of all, if you know the, for example, in this figure, if you know A has a higher potential than B, the current will flow from high to low. That's for sure. Right?
Okay.
But your question is good. In reality, you probably don't know which one is higher, right? Is that your question? Okay, and that's what we are about to do.
Okay.
All right. However, if you know that left is high, right is low, it will flow from left to right. That's guarantee. Okay. All right. Currents always flow from high to low potential. Okay. All right. Here we go. So this one is, once again, is like a summarize of the whole process. All right. You can always refer back to this slide if you want to sort of summarize the process. However, we're going to attack the problems right away. Here we go. And your friends ask a very good question. In reality, how can we tell which point has a higher potential than the other, because we haven't solved anything yet? So in this case, you just assume the direction of the current flow. That's it. And your equation eventually will give back the answer. What I'm saying is this. Okay, look at this one. Now you start seeing that this is a multi-loop, because you can see there are 2 loops, obviously. And in actuality, you can actually count 3 loops. When I say 3 loops, is this, you can do the left loop, the right hand loop, or actually the outer loop can be considered another loop. Okay, you guys with me, huh? So actually when you see it's a double loop configuration, but in terms of the actual looping, you can actually go around 3 choices. You can do left hand loop, right hand loop, or you can do the outer loop, the big loop if you want. Okay, very good. Now, because you don't know which direction of the current will flow, because in reality, there will be no I1, I2, and I3 at all. Okay, you see what I'm saying? So, just to be fair, and because I don't want to give you an impression that there are current flow in this already. So what actually you can think of is like, forget about this. You don't know anything, pretty much. Like, hey, Dan, I don't know. There's nothing going on here. I don't know. I don't know. I don't even know what current is, direction of the current is flowing on each part of this circuit. I don't know. Okay, you can, this is like, general problem will go like this. You just have like, hey, a circuit, give me the current flow through on each portion of this one. Okay, so the way of attacking this kind of problem is very simple. You start with the junction first. As you can see in this problem, you have two junctions, A and B. Okay, and it's a three-way street at this point. So once you have this junction having a three ways, what you can actually do is assign the current for each junction, each way. When I say each way, you can think here, the left side of this one, that is one single wire. Think of it that way. Okay, the left side of this one, that's a single wire. In the middle one, that's another single wire. Okay, and of course the right side of this one, let me get the blue. Here we go. See? All right. So now you have three junctions. I mean, at junction A, you have three ways that you can sort of split out. Okay? So all you need to do is assume that there are current flow on each wire in any direction that you want to. That's your choice, because we don't know anyway right now. So what I can assume is, I can assume that the current flow on this one to the right, let me call this I sub 1. You can assume the current flow on this middle wire to be I sub 2. And you can assume the current flow on this one is going to be I sub 3 if you want. In any direction you like, up to you. The final results will give you the final magnitude and direction of the current flow of I1, I2, and I3. Okay, sounds good. That's the first step. So you assign the current flow on each single wire that eventually they're going to join at the junction. But now when you look at this one, you apply the junction rule. Junction rule. And as you can see, you can pick junction A or junction B, doesn't really matter, because if you look at the junction A, at A, the current I1 is in, I2 is also in, I3 is also in. So the sigma I in must be equal to sigma I out. However, because your assignment, all three current are in, I1 plus I2 plus I3 must be all in, but no out. So out is 0. That's it. That's your equation number 1. You guys with me, huh? But if you look at the junction at B, you're going to get the same equation, because at junction B, the I1 is actually going to come out. I2 is come out. I3 is also come out. So you're going to get 0 equal to I1 plus I2 plus I3. Anyway, same equation. Doesn't matter. Pick one junction. Okay? And that junction will give you the relationship between the three currents that is flowing in each way from that junction. All right. Now, in your head, you start seeing the system that, hey, Dan, you are starting with the three unknowns at this point. I1, I2, and I3. So you need 2 more equations. And the other 2 equations come from loop rule. Now pick a loop. Any loop you like. Any loop. All right. So I'm going to try let's start from the obvious one, the left hand loop. So I'm going to assign this point to be X, A is already there. Okay, Y, M, N. Okay, here we go. You can put any name you like. So let's look at loop. So I'm gonna go X, A, B, N, X. You guys with me? That's the left hand loop. X, A, B, N, X. And now I am going to start walking, analyzing along this. So I'm gonna starting from X. Now I hit R1 with the current flow I1. Because I'm walking in the direction of the current flow, I say positive I1 R1. Okay, let's do the number substitution at the end. Keep walking. Now I'm at A. Turn. Now I'm passing through R2. However, now if you look at the R2, the current I2 is actually against you. I put negative sign. I2, R2. Keep going. Now I hit the positive ends of the battery. So I put the positive E2 of the battery E2. I'm done. Now I'm arriving at point B. Turn. Now I am hitting R1, having the current I1 through. But right now I am walking in the same direction as the current I1. So it's a positive I1 R1. Keep going. Now I'm at N. Turn. Now I'm hitting the negative ends of the battery E1. So I put a negative E1. Keep going. Now I am arriving at point X, which is the original point. I am completing the loop. Equate this whole thing equal to 0. Done. That's equation number 2. With me, guys? All right. But of course, because it's a 3 equations, I'm sorry, 3 unknowns, so you need 3 equations. So that means you need to pick one more loop. Okay? Just to showcase, you can pick any loop out of the 3 loops that you see. So let me do another loop for you guys. And just to show what it means by you can analyze the loop in any direction you like. I'm going to do the outer loop. But now I'm going to go counterclockwise just to showcase how it's done. So I'm going to start from the upper left corner. You can start at any point you like eventually. X, but now I'm going to go down here to N. So I'm going to do X, N, B, M, Y, A, X. So I'm going outer loop. The outer one over here, back here. Okay. All right. So now, once I know this is the loop that I'm going to analyze, I'm starting from X. Walking now, I'm walking down right away because I'm doing counterclockwise. I'm hitting the positive ends of the E1 on the left. So I say positive E1. Keep going. I'm hitting the point N, turn. Now I'm seeing R1 with the I1 through, but I am walking against the current. So it's a negative I1 R1. Keep going. Now at point B, nothing happened, nothing, turn. Now I'm seeing R1 with the I3 going through, but right now the current I3 is pointing in the same direction as my analyzing, so it's positive I3 R1. Keep going. Now I hit the negative ends of the E2 on the right, negative E2. Done. Now I am at Y, turn. Now I see another resistance R1 with the current I3 going through. But the I3 is pointing in the same direction as my walking, so it's a positive I3 R1. Keep going. Now I'm at A. Keep going. Now I am hitting another resistor with the current flow through, I1. However, now I'm going against the current. So it's going to be negative I1 R1. Now I am arrived at X. Complete the loop. That's my third equation. That's it. When I say that's it, means this is the 3 equations that you need to solve. Once you solve this for I1, I2, and I3, you solve everything in this pretty much circuits. When I say everything, once you know the current flow, you pretty much can calculate potential difference across. You can calculate anything on this circuits. Sounds good? All right, but just to show you the complete picture, all right, let's substitute the numbers in there because there is one more thing that you need to sort of understand once you get the final number. I hope this number is not too bad. Okay, so let's look at equation number 2. Let me substitute the number in there. Okay, equation number 2, I1 is there, R1 is 2 ohms, so it's going to be 2I1 minus 4I2 plus 6 volt plus 2I1 minus 3 equal to 0. Let me call this equation 2 stars. Okay, so all I need to do is just substitute the R1, R2, E1, E2 into equation number 2. Alright, so let me rearrange this one a little bit. So this one will give me 4I1 minus 4I2 plus 3 equal to 0. Alright, here we go. So that is my 2 star. Okay, let me call the bottom one 2 star. Okay, that's cleaner. Look. Okay, here we go. Very nice. Now, equation number 3. Oops, sorry. Equation number 3. Substitute the number in. E1 is 3. So that's 3. Minus R1 is 2. So it's 2I1 plus 2I3 minus E2 is, which is 6, plus 2I3 minus I1 R1, which is 2I1. Okay, so I'm just substituting at this point. So I try to go slowly to make sure I get everything correctly written. Now I'm at 4I3 minus 4I1 minus 3 equal to 0. That's my equation 3 stars. Okay, very good. All right. Okay, that's not bad. That's not bad. Okay. Okay, let me double check my number. Okay, 4I3 minus 4I1. Okay, minus 3 equals to 0. Okay, good. Okay, so now you can see that the equation number 1, number 2, and number 3 give you 3 equations for 3 unknowns. And now we can solve for this. Okay. I ran out of space a bit. Okay, but this one, we can add a page. So let me add one page here. Okay. Oop. Okay, let me add a page. Okay, so what I'm going to sort of go through with you guys today is, now let me rewrite that equation. I1 plus I2 plus I3 equal to 0. That's equation number 1. And this one, 4I1 plus 4I2 minus 3 equal to 0. That's equation number 2. Oh, minus, sorry. There you go. And equation number 3 is a 4I3 minus 4I1 equal to 0. Okay? All right. So these are 3 equations and 3 unknowns. And just slowly solve the system of equation. What I can do is, actually, I can eliminate some of the unknowns if I want. For example, I can just add how to do this. I can Um, um, yeah, eliminate I1, for example. Okay, so I don't know, is this a good or bad? Just to try. Okay, you guys can help me too, right? You guys help me solving this I1, I2, and I3. Okay. All right. Okay. All right. Either way will work. So I1 is just negative I2 minus I3. I just plug it in here. Okay, give me a minute to solve this. You guys should do along with me as well. Okay. So it's a negative. Okay, all right. And then 4I3 minus 4, yeah, something like that. Okay, so so this is my scratch paper at this point. Okay, so let me work on this one. So you're gonna get negative 8I2 minus 4I3. Okay, if you knows the answer, then just let me know. I don't know, is this the easiest way to get through or not? Oh, okay, 8I3 plus 8I2 minus 3. Okay, all right, so I just eliminate I1 from the system, and then I'm arriving at the two equations for the I2 and I3. Okay, my eye looks really bad. Okay, here we go. All right, so I can solve for the I2 and I3 now. So I can just, let me call this 4 and 5. So I just sum these two equations together to eliminate the I2. So I'm getting 4I3 minus 6 equal to 0. So I3 is just 3/2, 1.5 if you want. And done. Woo! If my calculation is correct, I hope it is. All right. Okay, let me sort of go through the end. All right. So once I found out what the I3 is, I can substitute back and then figure out what should be the I2. So I can substitute this thing back in here if I want. And that allow me to say that the I2, negative 8I2 minus 4, 3/2 minus 3 is equal to negative I2 minus, wow, this is weird now, 6. Okay, not too bad, I guess. Number is not nice. Okay, I hope it's just fine. Okay, that's good, I think. Negative 9/8. Am I doing it right? Okay, let me double check. 6 minus 9, 9/8. Okay, I'll keep that. Here we go. All right, so I already found out what the I3 should be and I2 should be. Once I found out the I2 and I3, I can plug it back into my first equation to figure out the I1. So I sub 1 is just negative I2, negative I3, and that will be minus, 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 so it's going to be plus, something like that. So it's going to be negative 3/2. Yeah. Okay, that's done. Can I pick the small loop to be? Yes. Okay, there's a question. You can pick the small loop as well. Yeah, you have 3 choices. You can pick the one of the 2 smalls or the bigger one. Pick 2. You just need to pick 2 out of 3. Yes. Okay. So what you're seeing over here is I'm just working through this system of equation to figure out the I1 and I2 and I3. So what's my point? Okay, my point is See this? See this? Of course, some of this you're gonna get negative currents flow because you assume that the current actually flow into the junction A, all three of them, which is in reality that's not possible that all the current will flow into the junction and disappear, right? Impossible. So that's why it says that actually the I2 is negative. When I say I2 is negative, what does it mean? It means your initial assumption that the current I2 is flowing up is just opposite to the final answer. Yeah, so that's answer your question as well. Which direction is also up to me? Yes, because in this case, because I assume the I2 is pointing up, but my numbers give me negative number. So it means in the final result, the I2 is actually going down. Okay, clear? So for some of you that pick the correct sign, so it means some of you might pick I2 to be down. You're going to get positive answer for this one automatically. Okay, same thing that happens to the I1. I1 is negative 3/2. So that means the I1 that I assume is pointing from left to right, in reality is pointing from right to left. Okay, so maybe some of you put like a perfect directions from the start. So your final result from your system of equation will be all positive. So this means your assumption of the current is already correct. Okay, but there's nothing wrong with picking the wrong direction because you're gonna get negative sign from the equation anyway. So that's no big deal. Okay, so I hope I make the whole argument of this whole thing clear that this is all you're going to have to face by applying Kirchoff's rule. Pick the junction to write down the equation that links the current flow. Pick the loop. Usually you have to pick 2 loops in this case if you have 3 unknowns because you have to have 3 equations to solve for 3 unknowns. Once you have that, do the loop analysis and plug in the number, solve the system of equations, you solve for all the currents flow in your circuits. See? Isn't that nice today? All right. It's kind of like, okay, it might be a little bit tedious, but it's guaranteed that you know how to do this for sure. And this will be in the final exam. Just 2 loop. I'm not going to go like crazy loop to give like 4, 5, 6, 7 equations of 7 unknowns. That's waste of time. All right. If you can just do this for 2 loops circuits, I think that's good enough. And that's show that you understand the Kirchoff's rule. Okay. Okay. All right. Let's do one more. Sounds good. All right. Just to double check that you understand how this one goes. Okay. Here we go. All right. So this, once again, you will be facing some multi-loop circuits. Okay. All of those R's, E's are given. There's no big deal. You can substitute numbers at the end. So what you would do is just doing the same thing as you did. In this case, you just, all right, there is 1 wire on the left, 1 in the middle, 1 on the right. Okay? Just assume current flow in any direction you like. Up to you. So I can assume that the current flow up on the left. Let me call this I1. And let me assume the current flow up in the middle wire, I2. And just to change the pace a bit, let me have the current flow on the right wire to be down, I number 3. Cool. All right. But you can pick any direction you want. Now, what kind of junction you have here? It's either junction A or junction B, but you already saw it. Either A or B will give you the same equation. So let's apply junction rule at point A. Okay, total in current must be equal to out current. What is in at A? You say I2 is in, I1 is also in, so it's going to be I1 plus I2, and the I3 is actually out, equal to I3. That is equation number 1. Cool. Now let's apply loop rule Okay. So now pick a loop. Now you probably want to pick the loop that you feel comfortable with. But actually, it's just going to be single loop. So I'm going to go M, N, O, P, just so we can communicate. So I'm going to try the right-hand loop. Sounds good? Just, change the atmosphere a bit. It's pretty much the same, actually. A, N, O, B, A. Okay. Let's go to the right-hand loop. All right. And let's write down the equation, guys. Okay, let me zoom in here a bit. So I'm starting from point A, going to the end. I'm going through R1 with the current I3, but I'm walking in the same direction as the I3. So it's a positive I3 R1. Okay, then I keep walking. I'm hitting the positive end of E3, positive E3. Keep walking. I see R1, another resistor, with the current flow in the same direction, so it's I3 R1. Okay, pretty good. Keep going. Nothing happens. Boop, at B I turn. I hit the negative end of E2. Negative E2. Keep going. Oop, I see another R2 with the I2, but right now I am going along with the I2. The I sub 2 is pointing up. I'm still walking up. So it's a positive I2 R2. I am arrived at A. I equate everything to 0. That's my equation number 2. Done. Okay. And now you can pick another loop. Just like your friend just asking, I can try the left-hand loop now. I can do 2 small loops in my analysis. So I can try, for example, I can do A, B, P, M, A. Or actually, let's do a backward. I'll go counterclockwise for fun. A, M, P, B, A, M. Okay, let's do that. Oh, too much. A. Sorry. A, M, P, B, A. Back to A. All right, start from A. Now I see R1 with my I1 going against me. So it's going to be negative I1 R1. Very good. So far so good. All right, keep going. Now I see positive ends of battery E1, positive end of the E1. Keep going. I see another resistor R1, but the I1 is still against me. So it's a negative I1 R1. Keep going. I'm at B, turn. See the negative ends of E2, so negative E2. Keep going up. Now I see R2 with the I2 pointing along with me. So that's positive I2 R2. Now I am back at A equal to 0. That's my third equation. That's it, guys. 3 equations, 3 unknowns. The rest, plug in the numbers, solve for the I1, I2, and I3. You will know the current flow in each portion of these circuits. Okay? All right, cool. So I think that's clear up what the Kirchoff's rule is and how to apply junction rule and loops rule. Actually, well, it's a rule that I think you guys already agree. Junction is just current in equal to current out. Loop rule is just every time you come back to the original position, whatever the potential that you have gone through must sum up to 0. Potential difference, yeah. Whatever potential difference that you have gone through must sum up to 0. Okay. All right, that's the correct expression for it. All right, sounds good? All right. This is a guarantee point in your final exam. Everyone should be able to do this 100%. So that's nice. Okay, so the rest you can complete numerical calculation yourself, and then I think I have one more for you to try. So if you want, don't forget to try this, and then I'll add some extra exercise for you guys, a little bit more for you to practice. But I think you only do like a few times, I think that's more than enough, right? That will already assure you that you know how to apply Kirchoff's rule, okay? And then so you can solve this kind of this type of problems with confidence. All right. Okay, cool. So now the last portion of this, all right? So it's just what happens if I add another element to the circuits, which is the capacitor. What you have seen so far, you only have either the battery or the resistor. What if you have the capacitor in it? All right, and the symbol for the capacitor is just reflects the parallel plate capacitor. It's just the two parallel lines in the symbol. Okay, so it's just a little bit different from the battery. The battery is just the two different lengths of the lines. The longer one is a positive ends. The shorter one shows the negative ends of the battery. But for the capacitor, you have two equal lines. Okay, and this one is a nice representations of the capacitor. Okay, so what you have over here is, if you try to draw a diagram for the capacitor, so what you're going to get is you have a symbol for that, connect to the battery like this. And when you do this, you go, hey, Dan, because the left ends of this one is a positive side of things, so that means you eventually going to give the left side of the capacitor to be positive potential as well, which it make perfect sense. In reality, the left plate will turn positive. And because the right plate connect to the negative ends of the battery, the right plate will turn negative, which is perfect. It reflects the actual system that you're going to create potential difference, generate electric field between the plates, on and on, blah, blah, blah. Okay. However, for the circuit analysis, we're not going to dig into the electric field anything anymore. What we're going to do is this. We're going to just add the C into your circuit. So what you had before, which is R and E, now you have C components. And we name this RC circuit. Straightforward. The only question that you're going to ask is, what happens to the circuit? Whoa, with this. Now let's talk about this briefly. What do you think will happen when you have the capacitor in it? Calculus is coming. All right, but we're not going to do calculus or anything in detail, but I'll just give you an idea. Okay, what do you think will happen when you have the C in your system? Okay, first of all, the capacitor is blank. Let's start from that. So when you have a blank capacitor, so it means blank say it means both sides of the plate is just neutral. So this means you have just an uncharged capacitor. So the capacitor doesn't have any charge on it. So you probably want to start the process by charging the capacitor. So I add the switch to it. So I can close down the switch to complete the whole circuit. And the charging process start its whatever charging process to start. Okay, that's better. So when I close the switch, then the charging process starts. Okay. Now let's imagine what would happen to the capacitor. Without the capacitor, first of all, without the capacitor, what do you think will happen? Of course, without the capacitor, okay, if you have just an R in your circuit, when you close down the switch, bam, of course, the current flow will be just E over R. Ohm's law. Right? With me, guys? If you don't have any capacitor on it, you slam down the switch, S, bam, the current will start flowing, bam. According to the Ohm's law, I equal to E over R. You're done. Okay? But now, you say, well, Dan, wait. Now you having the C in your system, what do you think it will happen? The answer is, okay, think about it. Oh, it's getting dark. The rain is coming. Whoa. Okay. All right. So when you have capacitor here, once you close down the switch, of course, the current will flow. Right? You say, Adan, what's the difference? It will have to flow. Okay? However, the thing is this. When the current start to flow, it means now this bottom plates turn a little bit more positive. The upper plate turn a little bit more negative, right? Because the current flow means, think of it like that is the charge flow into your capacitor. But now, you can think of the plate on the capacitor to be a room. When you have the current flow into the room, the next charge that try to enter the room will have a harder time entering. With me? Why? Because the same types of charge will repel each other. There is a Coulomb repulsion between the same type of charge. So when there are already some charges in the room, the new charge that try to enter the room will get pushed back a bit. So it's getting harder to get into the room the more charges are in the room. Make sense? So that means at first, seems like at the moment that you switch down the switch, the current will flow because the charge enter the room like, hey, nobody in the room, I'm free. But when the second charge try to enter the room, hey, there's a guy in there that's trying to push me back. So it's enter a little bit harder. Then when you start to collect more charges into the room, eventually the flow will getting smaller and smaller because the newcomer having a harder and harder time entering the room. Eventually the room will be full. So that means you about to fully charge your capacitor. So there will be no more currents flow anymore. With me? All right. So that means eventually the currents will start high. High means is E over R. The current will flow just like nothing happens. You don't feel anything. You mean the charge. The first guys that enter the room don't feel anything. So it feel like, hey, this is just like electrical wire. I don't feel a thing. But eventually, as t going to infinity, so when you wait a long time until the capacitor is fully charged, the current, oh, I shouldn't write like this. Okay, sorry. The current will approach 0. Nothing will flow anymore. Make sense? Okay, but now you can think in terms of the charge because we learn about this in capacitor. If you think in terms of about the charge that get into the capacitor will start from 0, of course. So if I try to draw a diagram, the amount of charge and the horizontal one is the time. Of course, you start from blank, so you start from 0 charge, and then you start to charge up your capacitor, so the charge will increase. But however, you said that the newcomer is having a harder time entering the room. So it means it's going to get harder and harder and harder and harder to increase the charge. And eventually, there will be no more additional charge entering the capacitor. So it means eventually you're going to hit some sort of like a maximum value of the charge. And that will be the Q maximum. That is the fully charged capacitor. Okay, make sense? All right, so I'll give you a sense of what is happening. And if you really want to see how this is going to happen in a quantitative manner, this is what is happening. All right, you have to write the equation that explains the change of the charge in your system. And it turns out, actually, I can apply Kirchoff's rule one more time. But once again, I don't want to sort of drag you through too much of the calculus, but at least you get an idea what is supposed to happen here. So actually this curve that is getting harder and harder to charge your capacitor is the solution of this equation right here. Okay, so for those of you that are really keen how to solve this one, you can go through this slide, but I'm just gonna jump right into the end. This is it, guys. Here we go. This is the equation that tells you how much charge is being increased as a function of time. And look at this. It looked like this. Not bad. This one looks bad, but it's not bad. Because, first of all, it has an exponential decay term in it. When I say exponential decay terms, means this term will approach 0 as t approaching infinity. You guys with me? Right? This term is an exponential decay. It's e to the negative power. So this means the longer you wait, the t will getting bigger. The bigger the t, the smaller this exponential term. So actually this means this term eventually will disappear over time. And see what you get at the end? It's the formula for the capacitance. Q max equal to CE. You guys with me? Yes. Yeah. Okay, so when you wait long enough, eventually this circuit, okay, will look just like you have no current flow, because we said when you wait long enough, there will be no more charging. Charge cannot flow into the room anymore. So when there's no current flow, whatever the potential difference that you put through, it will gonna go through just the capacitor. So when you know what is the potential across the capacitor, you can see the capacitance is just the ratio between the charge over the potential across. Or that's guaranteed that the Q max that you're gonna get is just CE or EC. See, it's already baked into this relationship automatically. Okay, sounds cool? All right, so let me erase this term. This dirty looking part right there. Okay, here we go. So once again, this term go to 0 as t going to infinity, and that lead you to maximum charge in the front. And what happened when time equal to 0? At t equal to 0, e to the 0 is 1, which is nice. This one equal 0. Oh, I'm sorry, equal 1. Sorry, guys. So as t equal to 0, e to the 0 is 1. 1 minus 1 equal to 0. So that means q at 0 is 0. That's perfect. That's what we agree. Because at the initial time, it's a blank capacitor. Nothing is happening. So the charge is still 0. But when you start the charging process goes on, then the charge will build up inside the capacitor. All right. And then when you wait long enough, you're going to get a fully charged on the capacitor of CE. Sounds good? All right. And once you know the charge that is flowing, you can actually calculate the current flow, because we know the charge is just, the current is just the charge per unit time. I can turn this into a calculus because this is a continuous function. So instead of doing just amount of charge per unit time, you just differentiate it with respect to time. So that means I can differentiate the upper equation to get the current, and that will give you the current flow. And that's agree with our understanding. At first, you start from the full current. See? Because in the first initial time, nothing's sort of like go against the flow of the current at all. So the charge will feel free, like, oh, I can just travel along the wire just like nothing happens. So once you switch down, bam, the current will start from the maximum value E over R. But then over time, it's getting harder and harder to get into the room. So this means the current is just going to get smaller and smaller over time. And that's what's happening right here. And when you wait long enough, the current will go to 0 with the same factor over here. It's the same exponential decay. So conclusion that you have over here is the charging process is exponential in nature. That's all I want from you. All right, don't worry about derivation of this. But the key is the exponential behavior of the charging process. Okay? And when I say exponential property of this one, look at this one. If I ask you this, guys, what should be the units of RC? ใกล้จบแล้วสู้ๆ เฮ้ยพอไหวไหมวันนี้ not too bad นะ it's kind of fun yeah okay what should be the units of RC guys very good because the upper one is time. I already mentioned this a couple times in this course. Whatever follow exponential, logarithm, sine, cosine cannot have any units. So the RC is also in time. So the product between the resistance R and the capacitance C give you second in units. So actually this give you how fast this charging process should do. That's why there is an RC numbers right here. Okay, you guys with me? Okay, so let me sort of compare between this. If you have 1 over e to the minus t over 10, and then you want to compare this with 1 minus e over t minus 100. Okay, and I have two curves. You think which is which? If this is A, this is B. So you think which curve supposed to be for the A and which curve supposed to be for the B? The answer is very simple. Here, look at this number, right? Because on the case A, RC is 10. Case B, RC is 100. So that means for the case A, it takes only 10 seconds for things to actually increase. Okay, but for the same amount, it will take the case B for 100 seconds to reach the same value. So that means A is going to be this and B is going to be the slower one. You guys with me now? So that's why they sort of like the RC to be the indicator of how fast the exponential will grow or diminish. That's why we name this RC to be time constant, because it's sort of like the constant of the circuit that tells you how fast things should get charged up, or actually eventually you'll see the discharging process. Same idea. Okay guys, so conclusion is actually the take home expression is just, okay, now we know it's exponential in nature. If you look at the charge will increase exponentially through this T over RC factor. If you look at the current will diminish with the same exponential decay factor, which is that RC thing. Okay, so that's kind of coincidence that when you look at the RC circuit, the RC actually is a characteristic time of the charging or discharging of the capacitor in the circuits. พอไหวไหมอันนี้ Is that not too bad? I hope. All right, even though it looks, I mean, the slide looks very, very calculus-ish, but you will receive this expression in the formula page in your final exam. So you don't have to memorize anything, but you just have to understand the characteristic of this expression. That's what it's supposed to be. Okay, try again, one more. Okay, now you don't even have to do anything. If I say, hey guys, let's start from fully charged capacitor and I want to discharge it. When you think of charge and discharge, I think the easiest example is the defibrillator. So it's the เครื่องกระตุ้นหัวใจ defibrillator. So when you saw it from whatever, well, the series on whatever TV, Netflix and stuff, when they have the patient's heart stops and they want to pump the heart again, they use that device that you have to put them together first, and there will be like a noise like that's kind of charging process. Okay, so whatever you have over here, that's you're charging the capacitor inside, and then you put this into patient's chest to discharge it. So you let go of the charge that you charge up, so it's just boom, and then you do it again, clear, and then that's the charging and discharging process. That's what it is. Okay, so starting from the fully charged capacitor, if you want to discharge onto the patient's chest, for example, what should be the discharging mechanism or characteristic? Yeah, don't need to do anything anymore. Exponential. Same exponential. Because you're going to end up with the same type of differential equation. You're going to hit the same way of solving this, and you're going to hit the same type of function at the end. So no doubt. Okay? So now, conclusion that I can draw here is, no matter what happens, exponential in nature, and the RC give you the characteristic time, how fast, how slow the charging or discharging will happen. Okay, I think that's good enough. All right, so if this is good, then let's answer some simple question. I think if this one will show up in the final exam, I think that will be straightforward. I hope. Okay. For example, if you have a maximum charge on the capacity is epsilon c, so this is your Q max. Or in the textbook, they just use capital Q. All right. How long does it take to charge an empty capacitor to half of its maximum value? If everything connect in series with the resistor, of course, we only do this type of circuits. Okay? So, no need to do anything. This is the charging. So you can refer to this expression right here. That's your charging process. Okay? So that means you can look it up in the first page in your final exam. It will look like this. But everyone now knows the main character of this one. Okay, so they want to know how long does it take to have a half maximum. So that means all you need to set this one to be CE over 2. Just half of it. Half of the maximum. Very good. So this one is just like you plug in the value of the charge on the left and solve for the T on the right. CE cancel. Yeah, very good. And now I can sort of manipulate this one a bit. So far so good. Okay, I can, well, take a logarithm, flip it over. So I can take log. You guys stay with me, yeah? Just remember logarithm a bit, yeah, from intensity of sound, all that stuff, yeah? So I just take natural log for the whole equations. Log of the inverse is just a negative log. Almost done. And that's it. Time that it takes is RC log 2. That's how you solve for the T. Okay? And of course, they can actually ask you to charge the capacitor up to whatever value of the charge that they want. All you need to do is just plug into this expression, and you can solve for T. How long does it take? Okay? And if you actually notice that RC is a time constant, you can actually answer this in the form of the time constant if you like. I mean, you can say it's a log 2 time constant if you want to. Okay, it's just like when you buy a donut, when you buy donuts, if you want 12 donuts, you can say like a dozen of donuts, something like that. Same thing over here. You can say time is RC log 2 second, or you can just say, hey, you have to wait log 2 time constants. So the time constant is just like a dozen. Yeah, so it's just a unit conversion, pretty much. Okay, all right. So I hope this conclude the characteristic of the RC circuits in a very brief manner, and I hope not too much to digest. And if you really want to dig into the derivation, you can look back in the handouts. พอไหวไหมวันนี้ not too bad. I hope at least the Kirchoff's rule is okay. All right, and add on top of this one, you add the capacitor to it, you get the RC circuit. The conclusion is it's an exponential in nature. So So it's still not too bad. All right. Okay, the last stop is this. Oh, what is this? Oh, okay, you can try this one. You just, instead of 1/2, it's 1/4. Okay, you can try this automatically. Okay, so before, we finalize everything, let's try this exercise. Okay, even though I have the rest of the stuff for the C, but I think we can conclude that later. Okay, because I don't want to add too much to today's lecture. I think this is about the good place to stop. Okay, so if I ask you just like this one, like a cool down question. Consider the circuit in the figure, and they ask you this, and I think this is what I'm going to pretty much, it's either previous kind of questions or maybe this one in the final exam. They say you have a system here, you have a circuit here. They say, what is the current through the battery when switch just after it's closed? So you can think of this one as like at time 0. What happened? We just throw down the switch. Or the second question, when the time is very long. So after the switch has been closed for a long time. Okay, what do you think about this one? Okay, actually this one is particularly just to confirm that you understand the character of the C in the circuits. Because my conclusion is this. At time 0, when the capacitor is blank, it behaves like a wire. You guys with me now? Right? When the capacitor is like, there's nothing in the room. The charge can just enter the room without any restriction, any obstruction, nothing. So the charge will not feel anything at all. So from the perspective of charges, it's just like, oh, I'm free. It's just like I'm moving in the electrical wire. So at time 0, the capacitor will behave just like an electrical wire. Oh, nice. On the other hand, when the capacitor is fully charged, completely charged to the maximum, you do not allow anything to pass it anymore. So there, it behaves like a broken wire because you do not allow any current to flow anymore. That's it. I think that's the final take of this one. If you understand these extreme conditions, it's just like you are talking about what is happening at the starting point, and you talk about what happening at the end point when t approaching infinity. That's like two extremes. And you know the function that connecting between the initial point and the infinity point, that's just exponential. Okay, that's the whole point. So what you have here is, I can say part A, your circuit will look like this. Isn't that nice? Right? Because your C behave like electrical wire. So now you can determine the current flow very easily. All right, and this one you say, oh, now I can do equivalent resistance and reduce that R down into just a single R. And then you can calculate the current flow. That's part A. For part B, well, Ajahn, because you have a fully charged capacitor, so it's broken. Ding, ding, ding. So there's nothing going on to the right. It's gone. So pretty much your circuit will reduce down to only just this. Nothing happened on the right. With me, guys? Okay, because it's already broken. It's open up. So nothing is happening out here. So your circuit is just this. So your I is infinity. It's just gonna be E over R. And I at 0 is just gonna be E over R over 2. Done. พอไหวไหมข้อสอบนี้โอเคไหม So if the question in the final looks like this, sounds reasonable. All right, so just to assure you guys that the question in the final will be straightforward and no sort of like calculus based question or anything. So it's either using the expression of the exponential function, or you just look at the behavior of the extreme points, what happening at time 0. You would just say, okay, the capacitor behaves just like electrical wire, and behavior at a very, very long time, infinite time. When the capacitor is fully charged, then there's no current flow. So it's like broken circuits. Okay, cool. All right, so that's finalize the whole thing. All right. Okay, guys. And I think I have, okay, you can try one more of this here if you want. Okay, but it's the same kind of questions. Okay, but it's just different rearrangement of the circuits a bit. Okay, so the last part of this one, I think, is a good reading. So I think you guys can try this. Okay, but you don't need to do it now. You just do it after you do some preparation of the final exam and things, and then you can add on top of this one a bit. All right, but the idea of this will be very, very easy to grasp if you already understood the Ohm's law and how the potential is being calculated from the Ohm's law and the property of the capacitor. All right, it will be easier that way. But I don't think I want to squeeze it now because it's already too much at this point, I think. All right, but I think I will have a chance to have you go through some exercises to practice, but just only a bit. All right, don't worry about the very hard questions. There won't be any hard questions here.